Okay, so the last talk of this session before a mini break is given by Matteo, and we're talking about
securing interruptible enclaves.
All right.
And this is a joint work with people from Leuven, Yolbio, Jan Tobias and Frank, and my supervisors, Matteo and Paolo. So let's start and let's see what's the problem with the isolation mechanisms that are around. And isolation mechanisms like processes, user kernel isolation, or enclaves are, well, broken. So, for example, processes are broken by Spectre. We have seen many talks today. User kernel is broken by meltdown, and perhaps a bit less famous, enclaves are broken by foreshadow. So it looks like that some advanced processor features like caches, speculative executions, interrupts in our case, break or well hinder the isolation mechanisms that are implemented in CPUs. So our idea was to have a language, supposed to have a language, H, which is an I language, we call it, that roughly models the mental model of the programmer, and it's an ISA implementing some given isolation mechanism, so an enclave, processes, etc. And suppose also to have a language L, which is actually H, plus some carefully implemented advanced feature, like in our case, interrupts. And our question was, well, it is possible to prove that the isolation mechanism in L is as secure as that in H, while maintaining the retrocompatibility, because you don't want that the programmer who writes their programs in H actually cannot reason anymore when his program is actually executed on some actual machine. So, well, we want to be sure then that if an attacker exists, like I started from here, if an attacker exists in a low language, then it must exist in a high language, and actually vice versa to guarantee for retrocompatibility. And maybe not everyone in this room will be with me, but full abstraction seems like a nice fit here. And so if two programs are indistinguishable for an attacker in the low language, and we write this in this way, then they must be indistinguishable for an attacker in the high language. And at the same time, again, for retrocompatibility, we also need the other arrow. In the full abstraction community, reflection is the arrow from the bottom to the top, and tells us that executions are actually retrocompatible. I already said like 3 times, but I want to stress it. And the other arrow tells us that okay. And preservation, so the other arrow tells us that any attacker in the low language has a corresponding one in the high language. So we are making sure that our isolation mechanism in the low language is not weaker than the one at the higher level. And, well, we argued that this is a nice general principle, but we actually instantiated it to a case study, which is enclaves extended with interrupts. In particular, maybe not everybody knows what an enclave is. For us, an enclave is an isolation mechanism to enable secure remote computation, of a module M. And the module M is actually composed by code that is remotely attested, that is run in isolation, and it's hidden. Though I might need to say that not every enclave ensures this. and data, so the data of the module that is considered as a secret, so it's hidden. And our focus for this talk will be just on isolation aspects, so no remote attestation. And in particular, we took Sancus, which is an enclaved execution system based on a Texas Instrument embedded microprocessor, which has a simple RISC instruction set. It's a 16-bit processor with very limited amount of memory, 64 kilobytes, split into protected and unprotected parts. That different instructions may take different time depending on whether their data comes from the memory or from the registers. And another thing is that we consider no caches, no speculative execution, and no interrupt enclaves for starter. And the question is, can we design, I would say in a principled way, a secure extension to Sancus enabling interruptible enclaves? So, well, it might seem like a trivial thing. I mean, everybody has interrupts, but as this paper from Yo and the others testifies, it's not so trivial. Because consider, I hope that you can see at least like the graphics, but consider an attacker, the guy here, and two modules, two protected modules. The first one does a 2 cycles instruction followed by a 4 cycles instruction. And the second one does the other way around, so 4 cycles instruction and then 2 cycles instruction. And supposed to have an attacker that is able to schedule and handle the interrupts, and suppose that he decides to schedule the interrupt right here. So after 3 cycles, part of the execution. And in this case, well, when the handler gets executed, you can actually see a difference in timing because his interrupt is handled at the end of this instruction for the blue guy, and at the end of the first instruction for the orange one. So, what's the problem here? There's a non-constant delay before the interrupt handler is invoked. And so what's the solution? Well, make it constant. And same setting as before, we pad by, in one case 4 cycles, and in one case 2 cycles, and then the attacker cannot discover anything new. Well, a question as a formal method person is that, well, are we done yet? And the real thing is that we are not done yet. Because, for example, the attacker could measure the time to end for an enclave and discover another attack. So, how do we ever know? And, well, we can try to apply full abstraction to this setting and see. So, instantiating what I said before to this setting, we get 2 models, Sancus I and Sancus Low. Sancus I is a core model of the original Sancus ISA, with no interrupts whatsoever, and for simplicity, just one enclave. And that's enough, actually, to have this kind of attacks. And the low-level language, instead, is Sancus Low, and is a model of a securely interruptible enclave with paddings as described before, plus some other bits, because, yeah, actually the paddings are not enough to guarantee security, but we need some other things. And let's see a bit more about Sancus Low. So, Sancus Low is actually Sancus I, so the same thing as Sancus I, plus interrupts that are handled in the classical way when we are outside an enclave, so the way you'd expect, and with paddings within the enclave execution, and with some attention to what happens when an attacker schedules interrupt during a padding that was in place. So, okay, we have Sancus I, Sancus low, but we are doing security, so we are interested in an attacker model. And so, who are the attackers? Well, an attacker is kind of strange here because it's comprised by the attacker's memory, so code and data for the attacker, and an attacker programmed device that can schedule, actually raise interrupts as he wishes. And we model this one as a deterministic I/O automaton. So what the attacker does to attack a module, well, it takes two modules, M and M prime, and runs them in an enclave, and tries to distinguish them with any mean that he can use. So if he can distinguish them, well, then it means that he can see somewhat inside the enclave and extract some secret. So its attack is successful. And okay, and now I won't go through all the details of the proof, but I think that the reflection part of the proof is actually pretty interesting, so I'll go over that. And in particular, we use a well-known technique of fully abstract traces to model what's observable in Sancus L, and we define a trace equivalence relation that tells us when two modules share the same traces under any context. And we put it here. Then we show this implication, so that if two modules are the same trace-wise, then there exists an attacker in Sancus law that can distinguish them. And this amounts to show that mitigation are indeed enough. And it actually, as I was telling you before, it actually requires some more than just paddings. Because, for example, you have to forbid the module to interact directly with the device. Or, again, you have, this is a bit more complex, but again, you have to make sure that registers are somewhat erased when an interrupt is to be handled, and that they are restored when the interrupt, when the handler terminates. But you could do that saving registers in memory, in protected memory, but this would expose the module to other attacks. So you should make sure that they are stored in a in a protected section of the microarchitectural state, so to make sure that attackers cannot discover those small things. And well, then a more classical thing, you have to show this arrow here. So indistinguishability at the eye level implies indistinguishability of traces. And you can do that by back translation, so by showing that if to trace you can find a trace that is different here, then it exists a context in Sancus I, a attacker in Sancus I that distinguishes the two modules. And by transitivity, you close the diagram and you get this implication. So the preservation part of the full abstraction. Others, nice bits of the proof. Well, you may wonder how we can build a back translation in a situation in which Sancus I has no interrupts at all. It never executes the interrupt ender. And this can be done because, of course, because we have back translation, but mainly because we have two isolation lemmata that tells us that interrupts or not, context executions cannot interfere with those of the modules and vice versa. And the other nice bit of the proof is that the attacker is actually very limited in terms of the quantity of memory it can take. And so the idea was to back translate the trace actually by using the device, the I/O device, to drive the attacker. So the attacker's code is like 25 bytes, fixed size. These pieces of code interact with the device and choose how to interact with the module to attack it. I can explain better later, if you like. And so, concluding, I have still plenty of time. The question was, can we enrich processors with new features by keeping retrocompatibility, which is fundamental, and without hindering security? And, well, we argue that full abstraction might be a nice fit in this setting. And to bake our claim, we actually proved the full abstraction between Sancus I, so the Sancus without interruptible enclaves, and Sancus Low, the one with interruptible enclaves. And what about the future? Well, we're not done yet. So, well, I'll start with the second one. Is it possible to prove the security of other extensions? For example, considering speculative execution, and how does that compose with what we already have? And also, people from the real world, let's say, are concerned with quantitative measures of security. So, can we adapt our framework to deal with secure enough systems? And finally, how does, full abstraction has to be compared with other security principles, because we argue that this indeed implies, our full abstraction proof implies a timing-sensitive non-interference preservation, but is it just that, or we actually preserve more, preserve exactly the same? We don't know. And that's it. Thank you.
Nice application for abstractions. Now, have we got any questions? So many. You have some more. Yes?
So I had a question about the padding. So one of the criticism that you have about that is that when you are padding, the knobs use less power than other solutions. So you can see it if you see the power consumption of your device. And that seems to be an issue.
Okay, we don't consider power consumption, but it could be. I mean, our model, well, in the microarchitecture state of your CPU, there's no power consumption. So
That's still essential.
yeah, that's true. I mean, but it's not in the model we consider. Yeah, not we just we're reaching the whole thing with observables. Right? Change your operational semantics to deal with that. You can probably use one of their principles. Yeah.
Can you say a bit more about the model of the processor you were using? Was it kind of fairly abstract and would apply to kind of any microcontroller you might hear about, or was it kind of very much a model of the MSP 430 and precisely the
It's
IO
a
device?
very concrete model of the MSP 430.
Or detailed enough I could simulate a program running on it?
Probably not, but it's actually pretty detailed. Of course, we model all the additional structures that, well, we actually have an implementation of that, and we model all the parts of the microarchitectural state that we needed to reach the original implementation. But for example, we have like a timer which is a natural number, but of course in the real world it would not be a natural number. So there's still some gaps. So I'm not sure you can actually simulate the real thing, but it's pretty concrete. So it would be hard to adapt that, but it could be done. But it's a little bit hard to do that like in a small amount of work.
So could you maybe say briefly what information your traces actually contain? That means
Yeah, sure.
information, yeah.
Our trace, I should have done a backup slide.
So the question is, what information is captured on the trace?
Okay, traces actually have. I was thinking of if I had some material ready, but no, I haven't. So actually, most of the things you are interested in are jumps into the enclave and jumps out of the enclave.
Okay.
Along with some meta information about that. So about the registers you are called with, plus some time information, and the register you return after the end of your enclave, plus the timing information that you need to model the time that you spent inside the enclave between two subsequent interrupts.
Okay, yeah. Yeah.
So you sum all them and you plus the paddings,
Yeah.
and you can show that this is enough to have. Yeah, plus the other things that I said, but this is enough to close this arrow here, to prove this arrow here.
Okay.
So there is no sharing of memory between the enclave and the context, or right?
Well, you could model that in two ways. One way would be the way you model that,
Which yeah.
and the other way is via registers. We have in the traces, we have registers.
Yeah.
So you could like imagine to add some more information, so registers and a shared piece of memory,
Yeah.
and that.
Yeah. So okay, cool. Well, we're perfectly on time. So we have a small break now. Thank you again.